Consider a reaction where we take a sodium atom, Na, and we add it to a chlorine atom to form sodium chloride, NaCl. We've previously learned what happens here is that sodium has 1 electron in its valence shell, and chlorine has 7 electrons in its valence shell. And what we've learned that what happens is that this electron from the sodium gets transferred to the chlorine, and sodium becomes a positive ion, and chlorine becomes a negative ion. And chemists use numbers to help keep track of what's going on. So we would say that sodium has a number of +1 and chlorine has a number of -1. And this is just basically where we use the numbers to track the movement of electrons during chemical reactions. These numbers written underneath here are what we call oxidation numbers. Okay, so oxidation numbers, numbers that chemists use to keep track of how electrons move in a reaction. Let's read a little bit more detail on that, and then we're going to discuss how we can figure out the oxidation numbers of different things. So the first thing to note is that the oxidation number of an element represents the number of electrons lost or gained by an atom of that element in a compound or an ion. So here we see this is the compound being formed, and these numbers represent the number of electrons lost or gained. So sodium has an oxidation number of +1, and if it has a +1, it's like having a +1 charge on an ion. It means it's lost an electron. So by losing an electron, you become a +1. Chlorine, in this case, has gained an extra electron, so we assign that an oxidation number of -1 because it's got 1 extra negative charge. So it's like how you would figure out the type of ion you're going to have. So chemists use them to keep track of electrons transferred or shared during chemical changes. Oxidation numbers make it significantly easier to recognize chemical reactions or recognize redox reactions. So we can identify whether redox, reduction and oxidation has happened by looking at oxidation numbers. There are a number of rules which help us figure out oxidation numbers, but I also want to be getting you to think in terms of common sense. It's not just about learning a set of rules. That can be handy as a backup, but I also want you to be able to think about what's going on so that we can figure out whether something is losing or gaining electrons and what type of oxidation number it's going to have. First of all, let's look at things like this. Let's look at, say, here is a magnesium atom. Here is a chlorine molecule. Here is a hydrogen molecule. And here is an iron atom. Now, the first thing I want to point out is what do all these things have in common? What they have in common is that they're all uncombined elements. They're not joined with anything else. They're uncombined elements. And if they're uncombined elements, they have not lost or gained any electrons yet. Okay, so that's the first thing to know. So the oxidation number of all of these things, they haven't lost or gained electrons. The oxidation number, and this is a rule sometimes people can forget. Common sense, what's happened? Nothing's happened to them yet, so they can't have an oxidation number. So uncombined elements have an oxidation number, On, equal to 0, always, uncombined element. That's the first rule. But I don't want to just give it to you as, oh, learn these rules. I want you to understand what's actually going on as well. But for our purposes, let's give it the number 1. This is rule number 1. All right, let's look at a different case here where we have magnesium, but this time it's a 2+ ion. And we have an O, 2- ion, and we have a H +1 ion, and we have an Fe, 3+ ion. The difference between these and the ones above is that these are all ions, which means they've already lost or gained electrons. So if they've lost or gained this many electrons, then it makes sense to say, okay, well, the oxidation number is going to match what ion they've become. How many electrons have they lost or gained? These are what we call simple ions, or monoatomic ions. And the rule here is that they just have a charge equal to the charge on the ion. So here we go. This has a oxidation number of 2+. So it has lost 2 electrons, become, sorry, I should actually say +2 there. It's not that important, but oxidation number +2. This has an oxidation number of -2. This has an oxidation of +1. This has an oxidation of +3. So hopefully you can see for simple ions, they've already lost and gained this many electrons, so the oxidation number has to match that. So that's rule number 2. O number equals the charge. So this is rule number 2. Now, if you want, you can pause this and start to make a list of these, but I do have it in the booklet if you're in my class. If you're not in my class, then it probably makes sense to make a list of these rules. If you want to do that, pause it now, take down the first 2 rules. All right, we're going to jump to the next one. Let's say we have this substance, NaCl, and LiCl, and we have KCl. What do all of these have in common? Well, what they all have in common is, well, they all have chlorine in them, but that's not really what I'm looking at here. What I'm looking at is sodium, lithium, and potassium. What these have in common is that they're all in group 1. So if they're in group 1 elements, group 1, that'll do. These are all metals. So again, you should know that from our previous studies that anything in group 1, sodium, lithium, potassium are all metals, and metals always lose electrons. And that's because they have very low electron negativities and very low first ionization energies. So it's very easy to remove electrons from these things. So definitely going to lose electrons and become positive ions. So they're going to have positive oxidation numbers. Now, the next thing is, how many are they going to lose? And again, this is where common sense come in. If they're in group 1 and they have 1 valence electron, and if they have 1 valence electron, then they can only lose 1 valence electron. So all of these will have an oxidation number +1. So that's the rule for these guys. If they're in group 1, they have an oxidation number of +1. So that's the rule. Group 1s have an ON oxidation number equal to +1, always when they form compounds. So they always lose 1 electron. So that's rule number 3. Next one, following on from that, guess what's next? The group 2 elements, magnesium. So magnesium chloride, for example, or we'll go to calcium. Calcium oxide is another example. So what these have in common is that these are group 2 elements. So we've got magnesium and we've got calcium. So again, what they have in common is that they're group 2 elements. They're also metals, low first ionization energies, low electron negativities, means they're going to lose electrons too. How many electrons are going to lose? Well, how many have they got to lose? Previous knowledge that we've learned, we're applying it here. So if they're in group 2, they're going to form +2 ions, or positive 2 ions, and that means they're going to have an oxidation number of +2. Okay, and that is rule number 4. So group 2 form oxidation number equal to +2. Again, if you need to, go ahead, pause the video and write down those rules. All right, I'm just making myself some more space. The next one is, guess what's next? Aluminium. Aluminium is in group 3. So say if we take aluminium chloride, AlCl3. Well, we're not going to do one underneath. We'll just do aluminium because, to be honest, aluminium is the only group 3 element really on our course. Well, guess what it's going to be? Again, it's a metal. It's got low first ionization energy. It's got a low electron negativity. Very easy to lose electrons. It's always going to lose electrons. And it's got 3 to lose. So it's going to become Al plus 3. So there's an extra rule. Group 3, they all become 3. All right. Again, pause the video, take that down if you need to. This is rule number, is it rule number 5? Rule number 5. All right, the next one is the first place where it really starts to get tricky. And I really don't think it is that tricky, but we're going to take our time with this one. All right, let's say we have a compound NaCl. Now, we already know something about this. We already know that sodium is in group 1, so it's going to have an oxidation number of +1, like this. Which means that overall, that the charges of the things inside it that make it up have to add up to 0. So there's no charge. If there was a charge here, I would see a sign up here, maybe a 2- or something after this whole thing. But there's nothing here, which means that this is 0. So if this is 0, the oxidation numbers, and the sum of the oxidation numbers have to add up to 0. So neutral compounds, the rule is the sum of oxidation numbers has to equal to 0. Now this is a very easy case, this first one to do. If sodium is +1, that means that chlorine has to be -1. So +1, -1 add up to 0. So that's pretty straightforward. Let's look at an example of, instead of sodium chloride, we have magnesium chloride, MgCl2. We know that magnesium, so you'd be tempted to say that chlorine, oh, that has to be -2 then. Okay, I can understand why you might think that, because I just said neutral compounds have to add up to 0. But there are 2 atoms of chlorine, and that makes a difference. There are 2 atoms of chlorine. So I'm going to show you what I do to get around this. I do the totals. I'm going to say the total sum of oxidation numbers has to add up to, which is where I take the oxidation number and I find out what's the total charge for the magnesiums. So I do it up top here. Well, there's only one magnesium, and that one magnesium has a +2 oxidation number. So that means +2. And I do my totals up top here. So I do my totals up top here. So +2, how do I make +2 turn to 0? Well, if my magnesium is +2, to make this add up to 0, that means my chlorines altogether, the total has to be -2. So up top, that is correct now. +2 minus 2 equals to 0. But then what I need to do is find out what one chlorine would be, because when I'm writing the oxidation number down below, I'm talking about if I just have one chlorine. So the total for the chlorines is 2, is -2, but there are 2 of them. So what I need to do is divide and write down the oxidation number of chlorine, the element chlorine underneath. So -2 altogether, but there are 2 of them, which means oxidation number of chlorine is -1 here. So each chlorine atom is -1. Together they make -2. That there is where it gets a little bit tricky. I'm going to get you to do one now. Actually, I'm going to get you to pause the video and write down that rule there, rule number 6. Okay, neutral compounds, the total sum has to add up to 0. Pause the video, write that down. Okay, so I'm going to give you one to do now. So this one, AlCl3 for me. All right, I'm just going to make that clear. That's a 3. Pause the video, do that now. Okay, I'm hoping that what you said was that the oxidation number for aluminium, it's in group 3. So this is the way you're thinking about it. Okay, you can remember the rule, oh, aluminium is +3, but it's better, just go to your periodic table and look, you'll see it's in group 3. It's a metal, it's going to lose electrons, so it has an oxidation number of +3. Now, most of you, or some of you might have said, okay, well, if aluminium's +3, chlorine has to be -3. That means they add up to 0, but it's not that simple because there are 3 chlorines. So remember what I told you? We've got to go to the top to do your totals. Okay, so go to the top here, do your total, and make it add up to 0. If you didn't do this, pause the video and do it now. Do the totals, make them add up to 0. Okay, so this is what you should have had. Aluminium is +3 because there's one of them. And that means that the chlorines have to be -3. Good. Well done if you got that right. But now we need to find out what the oxidation number of the element chlorine is. There are 3 of them. So each one, if there are 3 of them, to get to -3, each one has to be -1. And this is what's important when they ask you what's the oxidation number of each element. This here is your answer. That's your answer. That's the important bit. If you put this in as your answer, it's going to be wrong. Okay. All right. Let's take it up one more level now and let's do a harder example. What happens if we have 3 elements in our compound? So say, for example, K2COR2. Actually, do you know what? We're probably not. I need to give you a few more rules before we can do that one. Apologies about that. Right. So that's the rule for neutral compounds, and it's probably the most important of the rules so far. Let's look at the next rule. Here is KCl have elements from group 7: chlorine, bromine, and fluorine. Non-metals gain electrons. That's what they like to do. And these are the halogens, which means that they're highly electronegative. So they're in group 7. Group 7 negativity, which means they're going to gain electrons. Again, be sensible about it. What group are they in? How many electrons are they going to gain? You should be thinking, something should be going in your head now. They're all going to gain 1 electron to become -1 ions, all -1, because they're the most electronegative. So that means that any group 7 element is usually going to be -1. There are a few exceptions, which we'll see later on. But in this case, all of these are taking electrons from the potassium and become a -1. The oxidation number of them is -1. So that's a general rule. Again, that's rule number 7. So in green. The next one is hydrogen. So let's look at lithium hydride, sodium hydride, hydrogen chloride. Funny, because it depends what it's combined with. In the case that it's combined with a metal, so for example, lithium and sodium, we know the rule for these is they always lose electrons. So they become +1 ions, definitely, that's for sure. Well, if they're becoming +1 ions, then that means that hydrogen has to be a -1 oxidation number. It has to have a minus. It gains electrons. It takes electrons from the metals. Okay, let's look at the other case though. Here we have hydrogen with a non-metal. In this case, chlorine in group 7 is a -1 ion, has a -1 oxidation number, and bromine is a -1 ion, has a -1 oxidation number. which leaves it so that in these cases, hydrogen is +1 oxidation number. So very unusual that it depends what it's joined with. Okay, so that's group A. How do we summarize that rule? We summarize it like this. So hydrogen, non-metal, like chlorine, fluorine, magnesium, calcium. Okay, so that's the rule for hydrogen. Now, there are just a couple more. Okay. The next rule that we're going to look at is oxygen. So let's say we take magnesium oxide, we take lithium oxide, and we take, let's just do these first. Okay, magnesium oxide and lithium oxide. In this case, magnesium's in group 2, it's going to have a +2 oxidation number. It's very easy to see here, then that means oxygen is -2. That should make sense too, because if you look at oxygen's group, it's a non-metal. In group 6, it's going to gain 2 electrons, usually. Okay, it's going to gain 2 electrons and become -2 ions. So -2 makes sense. In this case, lithium is in group 1, it's a +1 ion. Don't forget to do the totals up top because there's more than one of these. So the totals for lithium is oxygen has to be -2, so the sum equals to 0. And again, oxygen is a -2. So a rule here for oxidation number equal to -2, usually. There are a few exceptions to this. Let me show you the exceptions. The first case of an exception is in the substance hydrogen peroxide, H2O2. In hydrogen peroxide, oxygen is bonded with hydrogen. So hydrogen is going to give electrons to the oxygen. Oxygen is going to take electrons from the hydrogen. But each hydrogen only has 1 electron. We learned that before, as an atomic number of 1 has only 1 electron to give away. So the only thing it can do is become a +1 ion, giving away 1 electron. The totals then, up top here, is +2 for the hydrogens, which means the total of them, which means -1 oxidation number. So it's a little bit unusual, okay? So that is peroxide. This substance is called hydrogen peroxide. So that's our one exception. So let's make a note of that here. Exception in peroxide equals to -1. There is one other time that oxygen will not be -2, and that is if it's combined with fluorine. Fluorine is the only element on the periodic table that's more electronegative than oxygen. And what that means is when we put these two things together, it's the fluorine that's going to take the electrons. All the other times, oxygen took the electrons to become a negative ion, took the electrons, but this time it can't because it's not physically able to take electrons from the fluorine, which means the fluorine is in group 7 becomes -1. Total charges from the fluorine is -2 because there are 2 of them. And we now know that the sum has to add up to 0. So that means that oxygen, unusually in this case, has to be +2. There is another exception. Fluorides is equal to +2. +2 usually. Okay, so where are we? That's rule number. That's rule number 9. Sorry, rule number 9, right there. All right, there is one more rule. I'm going to pause the video and let you write down any rules that you haven't written down yet. There's one more, and that is in the case of something like this. So say we have CO3 2- or PO4 3-. Both of these things we've learned before. These are ions, but they're a group of atoms that carry a charge. So not just one. So this is the alternative, O2-. This is a single atom that carries a 2- charge. This is a group of atoms that carries a 2- charge, or that carries a charge. These are what we call meaning many, polyatomic, many atoms, polyatomic ions. The rule here is that you will go ahead and you assign the oxidation numbers in the way that you know, but that the totals have to add up to the charge on the ion. What do I mean by this? Let's take an example. Here, oxygen, as usual, is -2. It's not combined with, in a peroxide, it's not combined with fluorine, so it's always -2. Up top, we do the totals. So there are 3 oxygens, so 3 minus 2s is a total charge on the oxygens of -6. Now, normally we say for a neutral compound, the total sum of charges has to add up to 0. But in this case, it doesn't add up to 0, it adds up to the charge on the ion. So it adds up to -2. So what do we have to add to -6 so that we'll be left with -2? The answer here is we have to add +4. +4 minus 6 gives us -2. There's 1 carbon, which means the oxidation number of carbon is +4. The rule here is that the sum of oxidation numbers equals to the charge on a polyatomic ion. You try the second one. Pause the video and try PO4 at 3- for me now. Pause the video, do that. Okay, so here is -2 on the oxygen. There are 4 of them. That gives us a total charge of -8 on the oxygens. And we have to let the sum of the totals on top add up to -3, because this is a 3- here. So it has to add up to -3. So what do we put on phosphorus so that they'll add up to -3? Okay. Some people, the mistake I see people make here is they say, oh, they need -5. But if we think about it, the sum of -5 and -8 is -13. It's not -3. This has to be a +5. +5 -8 gives you -3. Phosphorus +5. And it should make sense. Phosphorus is in group 5, so it's got 5 valence electrons that it could lose. That is the set of rules. Again, hit the pause video, take that down if you want to. Alternatively, that is summarized in this table here, So if you didn't take all that down, again, what it might be a good idea here is to pause the video and take it down from here. This is a more summarized version, but I always like to work from examples rather than just give you a table to learn. Remember, it's a combination of learning rules, but also applying common sense about what group things are in, how many electrons are they going to lose or gain electrons? Are they metals or non-metals? Are they going to lose or gain electrons? What group are they in? How many valence electrons have they got? And also, sometimes you have to consider electronegativity, first ionization energy, to help you figure out are they going to gain or lose electrons. All right, let's again start by applying a few examples. I'm going to do a few of these examples for us, just so you see a few more of them. All right, the first one here is, what's the oxidation number of aluminium in Al+3? This one is very easy, it's done for us already. Al+3, the rule here is that this is a monoatomic ion. It's a single ion atom with a charge. So oxidation number has to be equal to the charge on the ion. So it's +3. That one's very easy. And it's this rule where, here, monoatomic ion. Charge on the monoatomic ion is equal to the oxidation number. Let's do the next one. Deduce the oxidation number of nitrogen in HNO3. So that works like this, HNO3. That's the first thing you do, is you write down the compound like this. The second thing you do is you write down the oxidation numbers of the things you know. Tip here, always start with oxygen if there is oxygen, because oxygen is pretty always -2, with a couple of exceptions again. In fluorides or in peroxides, oxygen is always -2. So I'm going to start by writing that down here, -2. The next thing that I want to point out is always do the totals up top. Okay, be very careful that we're not trying to just work from the bottom. Do the total up top. So lay it out like this, total up on top. So the total of them and each one is a -2. What's the next thing that we know? The next thing we can work out here is the hydrogen. Hydrogen is combined with non-metals, and hydrogen is combined with non-metals. It's positive. Total +1 because there's only one of them. The next rule to apply here is that the sum up to 0. So +1 -6. The one squeeze in the middle here, 6, should add up to 0. If you're not sure about that, get your calculator out and figure it out. There is 1 nitrogen. Total charge for nitrogen is +5, and there's only 1, so that means nitrogen is +5. And to clarify that, it asks us to do that. So it says nitrogen equals +5. That's our final answer. In fact, we should probably say the oxidation number of nitrogen is +5. All right, let's do another one. Deduce the oxidation number of sulfur in H2SO4. H2SO4. So first thing to do is write down your compound. The next thing to do is start assigning the oxidation numbers. Again, I'm starting with oxygen because it's the easiest one to begin with, -2. It's always -2. Totals up top, -8 on the oxygens, 4 -2s. Remember the rule? Totals on top have to add up to 0. We know as well, switching pens for hydrogen. Hydrogen combined with non-metals becomes +1. There are 2 of them, so totals from that is +2. So make the top add up to 0. +2, what's the middle one got to be? Simple algebra, shouldn't be very complicated for us there. +2, get your calculator out if you're not sure. +6 is what that has to be. And sulfur equals +6. Keep going. What's this one? I see a polyatomic ion. So it's a group of atoms with a charge. So 4 minus. Again, starting with oxygen, -2. There are 4 of them. -8 is the total. Rule here is for a polyatomic ion, you have to make the sum add up to the charge on the ion. This is a -1. So what I've got to do is figure out what can I make the manganese to make this add up to -1. So if I make this a +7, +7 minus 8, it gives us -1. So that there is the oxidation number of manganese. Next one, a 3-atom compound, NaClO. NaClO. Okay, again, I'm starting with oxygen, -2. Total up top is -2. Pretty straightforward. Sodium is in group 1. It's always +1. Total +1. Now, rule here is the sum has to add up to 0. So we've got +1. This one also has to be +1. So this is really strange because chlorine's in group 7. We expect it to be -1. But why is it not -1? Well, oxygen, negative. It's going to take the electrons from the chlorine. So we assume, or we write that chlorine has lost the electron to the oxygen. And it has an oxidation number of +1. So chlorine, so our oxidation number of chlorine equals +1. So a bit unusual because group 7 are normally -1, but when it's combined in this case with the more electronegative oxygen, it's the oxygen that gains the electrons, and the chlorine has to give it up. Right, the absolute 100% best way to learn this stuff now is to practice. It's the best way, and practice lots of examples. So what I'm going to do is I'm going to give you a pretty big table of stuff that I want you to practice out now. We're just going to do the first 2 for you, okay? So again, it says determine the oxidation number for all the elements in the following compounds, and your teacher is going to lead and do the first 2. Okay, so again, we've got lithium chloride. Very simple. Lithium's in group 1 +1. Chlorine's in group 7, and there's 1 of them here, so it's -1. Now, again, the best way to do this, that's very easy because there's 1 lithium and 1 chlorine. The next one, ZnI2, you're going to have to take it out to the side here and actually write it down. So ZnI2. Okay, so again, not ones we've come across before, so you're going to have to get out your periodic table, look up the groups and see can you find out anything here. Pause the video. Oh, sorry, I'm doing this one for you, never mind. Okay, so iodine, I is in group 7. So the rule here is, and this is a metal, so it's going to lose electrons. So the iodine is going to take the electrons. Sorry, making a mess here. ZnI2. So I is 1 oxidation number. The zinc has to have a +2, so that is +2. Go back to my table, fill them in. +2. Right. What I'm going to do is I'm going to, sorry, on my table. Now, where is that table? Here it is. This is not doing what it's supposed to do. Okay, I've zoomed in, so I hope that you guys can see all the questions there. I'm going to get you to pause the video and work through all of them examples. Again, it's designed so that it builds from easy ones into harder ones. So the hardest ones down the bottom, and it's building up your skills through easy examples, working into harder ones. So it's important that you do them all. I know it's a lot of work, but it will pay off. It will stick with you if you do them properly. So pause the video, work your way through them, and do those now, please. So pause the video. All right, so you should only be watching if you have worked your way through all of them examples and you have them done. Okay, so there's actually one here I don't want you to worry about. I forgot to tell you, and that's that one. We're going to cross that one off because it's just too hard for us at this level, and it doesn't really need to be there. So I'm just going to go ahead and I'm going to scribble that one out. And I hope you didn't spend too long working over that one. All right, so all the rest here, you should be able to do from the rules that we've gone through. What I'm going to do is I'm going to flick to the answers. Again, do not lie to yourself. If you're just taking the answers down from the thing I'm going to show you and you're not actually checking them and you haven't tried them, you're not going to learn anything from doing that. All right, so I'm flicking to the answers. Again, I remind you, this is only for you to give yourself confidence that you know how to do these. It's not for you to copy the answers. You're not going to learn anything by doing that. All right, so this here is the table of completed answers. So pause the video, go through your answers, and hopefully you got these correct. Anything you didn't get correct, guys, you need to go back and check some of the rules again. If you've got any specific questions, you can put them into the questions below the video here, and maybe I can make another video clarifying something for you if you're stuck. If you found the video helpful and you're confident with oxidation numbers now, please do give it a like, because it helps the channel, it helps other people find it. Other people may have the same difficulty as you, and this will help them find the video and help more students. That's what the videos are for. All right, guys, that is it. I will see you in the next one, where we'll be taking these oxidation numbers and we will be applying them to full reactions so we can track oxidation and reduction. All right, we'll see you in the next video.